The National Electrical Code, or NEC, doesn't specifically mandate grounding bushings with bonding jumpers for feeders supplying critical care areas. Section 517.14 of the NEC outlines the general bonding requirements for these critical care areas. Let's delve into the details of NEC 517.14 concerning panel boards. For normal panel boards, 517.14 paragraph states that the non-current carrying metal enclosures of normal panel boards supplied by a feeder must be grounded by one of two methods. Firstly, by bonding the enclosure to the grounded neutral conductor or equipment grounding conductor within the panel board, or secondly, by connecting the enclosure to a grounding electrode conductor, sized according to Table 250.66 of the NEC. For essential panel boards, 517.14 paragraph B requires that the non-current carrying metal enclosures of essential panel boards be grounded either in accordance with 517.14 paragraph A, which we just discussed, or by one of the following additional means. Firstly, by a ground fault current path from the grounded neutral phase leg or equipment grounding conductor connected to the grounding terminals in the panel board, or secondly, by a separate copper ground fault current path of not less than number 8 American wire gauge. While the NEC does not offer specific sizing requirements for bonding jumpers in critical care zones, it does provide guidelines for sizing grounding electrode conductors, or GECs, within Table 250.66. These guidelines can serve as a starting point for sizing bonding jumpers. Considering a feeder to a normal panel board, if the feeder is sized over 1000 kc mil copper or 1250 kc mil aluminum, a number 8 American wire gauge minimum copper bonding jumper is required. Regarding a feeder to an essential panel board, if the feeder is sized over 1000 kc mil copper or 1250 kc mil aluminum, a ground fault path of not less than number 8 American wire gauge is required. Although the NEC does not mandate the use of grounding bushings, they are often recommended as a best practice to guarantee a reliable grounding connection. Grounding bushings offer a convenient and secure means of connecting bonding jumpers to the panel board enclosure. The NEC does not define the extent of a critical care area. Determining these boundaries is the responsibility of the design engineer. It's reasonable to extend the critical care area to encompass the feeders that supply power to that area. This ensures that all electrical equipment within the critical care area is properly grounded and protected. The engineer's insistence on extending the critical care area all the way back to the service is a design choice. The important thing is to ensure that all electrical equipment within the defined critical care area is properly grounded and protected. Keep in mind that the NEC does not specifically define the extent of a critical care area, leaving this determination to the design engineer. When sizing bonding jumpers, reference Table 250.6E6 for guidance. Remember that if the feeder size exceeds 1000 kc mil for copper or 1250 kc mil for aluminum, the NEC mandates a minimum number 8 American wire gauge copper bonding jumper. Always consult the latest edition of the NEC and local amendments for the most accurate and up-to-date requirements. Ensure your electrical installations adhere to all applicable codes and regulations to maintain safety and compliance. A thorough understanding of grounding and bonding principles is essential for all electrical professionals. Continuous learning and staying current with code changes are crucial for ensuring safe and reliable electrical systems, particularly in sensitive areas such as critical care facilities. When working with electrical systems, always prioritize safety. To energize circuits before working on them, use appropriate personal protective equipment, and follow established safety procedures. Electrical work should only be performed by qualified and licensed individuals. Proper grounding and bonding are critical for preventing electrical shock hazards and ensuring the proper operation of electrical equipment. A well-designed and properly installed grounding system provides a low-impedance path for fault currents, allowing protective devices to quickly clear faults and minimize the risk of electrical hazards. Bonding ensures that all metal parts of an electrical system are at the same electrical potential, reducing the risk of shock hazards. In critical care areas, where patients are particularly vulnerable, the importance of proper grounding and bonding cannot be overstated. These measures help to minimize the risk of electrical leakage currents that could interfere with sensitive medical equipment or pose a shock hazard to patients. In addition to the NEC requirements, it's also important to consider any specific requirements or recommendations from the equipment manufacturers. Medical equipment often has specific grounding and bonding requirements that must be followed to ensure proper operation and patient safety. Regularly inspect and test the grounding and bonding system to ensure that it is functioning properly. Over time, connections can loosen or corrode, which can compromise the effectiveness of the grounding system. Regular maintenance and testing can help to identify and correct any potential problems before they lead to a safety hazard. When making any changes or modifications to an electrical system, always ensure that the grounding and bonding system is properly maintained and updated to meet the new requirement. Failure to do so can compromise the safety and reliability of the electrical system. Always consult with a qualified electrical engineer or inspector if you have any questions or concerns about grounding and bonding requirements. They can provide guidance and ensure that your electrical system is compliant with all applicable codes and regulations. Proper grounding and bonding are not just a matter of code compliance, they are essential for ensuring the safety of people and property. By following best practices and adhering to the NEC requirements, you can help to create a safe and reliable electrical system that protects against electrical hazards. Remember to always prioritize safety when working with electrical systems. Proper training, qualified personnel, and adherence to established safety procedures are essential for preventing electrical accidents and injuries. Grounding and bonding are fundamental concepts in electrical safety. Grounding provides a path for fault current to flow back to the source, allowing overcurrent protection devices to operate and clear the fault. Bonding connects all non-current carrying metal parts of an electrical system together, creating an equipotential plane that minimizes the risk of shock hazards. A well-designed and properly installed grounding and bonding system is essential for ensuring the safety and reliability of any electrical system. The size of the grounding electrode conductor, or GEC, is determined by the size of the service entrance conductors. Table 250.66 of the NEC provides the sizing requirements for GEC based on the size of the service entrance conductors. The equipment grounding conductor, or EGC, provides a path for fault current to flow back to the source from equipment enclosures and other non-current carrying metal parts. The size of the EGC is determined by the size of the overcurrent protection device protecting the circuit. Table 250.122 of the NEC provides the sizing requirements for EGC based on the rating of the overcurrent protection device. Bonding jumpers are used to connect different metal parts of an electrical system together, creating an equipotential plane. Bonding jumpers are typically sized according to Table 250.66 of the NEC, but in some cases a larger size may be required to provide adequate fault current carrying capacity. Grounding electrodes are used to connect the grounding system to the earth. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. The NEC specifies the requirements for the installation and connection of grounding electrodes. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock hazards. GFCIs work by monitoring the current flowing in a circuit and detecting any imbalances that could indicate a ground fault. If a ground fault is detected, the GFCI will quickly interrupt the circuit, preventing electrical shock. Arc fault circuit interrupters, or AFCIs, are devices that are designed to protect against fires caused by arcing faults. AFCIs work by monitoring the current flowing in a circuit and detecting any abnormal arcing conditions. If an arcing fault is detected, the AFCI will quickly interrupt the circuit, preventing a fire from starting. Surge protective devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. SPD work by diverting excess voltage to ground, protecting sensitive electronic equipment from damage. Regular inspection and maintenance of electrical systems are essential for ensuring the safety and reliability. Inspections should be performed by qualified electrical professionals who can identify and correct any potential problems. Maintenance tasks should include tightening connections, cleaning equipment, and testing protective devices. Electrical safety training is essential for all workers who work with or around electrical equipment. Training should cover topics such as electrical hazards, safe work practices, and the proper use of personal protective equipment. Lockout/tagout procedures are used to prevent accidental energization of electrical equipment during maintenance or repair. These procedures involve disconnecting the equipment from its power source and attaching a lock and tag to the disconnect switch to prevent it from being turned on. The NEC is a comprehensive set of standards for the safe installation of electrical wiring and equipment. The NEC is updated every 3 years, and it is important for electrical professionals to stay current with the latest changes. Local codes and regulations may also apply to electrical installations. It is important to check with the local authorities to determine what codes and regulations are in effect in your area. The National Fire Protection Association, or NFPA, is a non-profit organization that develops and publishes codes and standards related to fire safety. The NFPA's codes and standards are widely used in the United States and around the world. Underwriters Laboratories, or ALL, is an independent organization that tests and certifies electrical equipment. UL-listed equipment has been tested and found to meet UL safety standards. The International Electrical Testing Association, or IETA, is a non-profit organization that provides accreditation for electrical testing companies. IETA-accredited companies have demonstrated that they have the knowledge, skills, and equipment necessary to perform electrical testing safely and accurately. Certified Electrical Safety Technician, or CEST, is a certification offered by the National Association of Safety Professionals, or NASP, that verifies an individual's knowledge and skills in electrical safety. A CEST certification can demonstrate your commitment to safety and enhance your career opportunities. It is vital to remember that electrical work can be dangerous and should only be performed by qualified and licensed individuals. Following safe work practices and adhering to all applicable codes and regulations is essential for preventing electrical accidents and injuries. The primary function of the grounding system is to provide a lower impedance path for fault currents to return to the source, enabling the rapid operation of overcurrent protective devices like circuit breakers or fuses. This swift action minimizes the duration of fault currents, reducing the risk of electrical shock, equipment damage, and fire hazards. The purpose of bonding, on the other hand, is to establish an electrically continuous and conductive pathway among all metal parts that are likely to become energized. By connecting these parts, bonding ensures they are at the same electrical potential, eliminating voltage differences that could pose a shock hazard if a person comes into contact with 2 or more metal surfaces simultaneously. The combined effect of grounding and bonding is a comprehensive safety strategy that protects individuals from electrical shock and minimizes the risk of damage to electrical systems and equipment. Grounding electrodes are conductive objects buried in the earth to provide a connection to ground. Common types of grounding electrodes include ground rods, typically made of copper or copper-clad steel, buried horizontally or vertically in the ground. Ground plates, which are metal plates buried in the earth, and metal underground water pipes, under specific conditions outlined in the NEC, can also serve as grounding electrodes. The selection and installation of grounding electrodes must comply with NEC requirements to ensure effective grounding. Grounding electrode conductors, or GECs, connect the grounding electrode to the electrical system's grounded conductor, typically the neutral conductor, at the service equipment. The GEC carries fault current from the electrical system to the grounding electrode, facilitating the operation of overcurrent protective devices. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. Equipment grounding conductors, or EGCs, provide a low impedance path for fault current to return to the source from equipment enclosures and other non-current carrying metal parts. EGC are typically wires or metal raceways that are run along with the circuit conductors. The size of the EGC is determined by the rating of the overcurrent protective device protecting the circuit, as specified in NEC Table 250.122. Bonding jumpers are conductors used to connect different metal parts of the electrical system together, creating an equipotential plane. Bonding jumpers are used to bond metal raceways, enclosures, and other metal parts to the grounding system. Bonding jumpers are typically sized according to NEC Table 250.66, but in some cases, a larger size may be required to provide adequate fault current carrying capacity. Grounding bushings are fittings used to connect metal raceways to equipment enclosures or grounding electrodes. Grounding bushings provide a secure and reliable connection between the raceway and the enclosure or grounding electrode. Grounding bushings typically have a set screw or other mechanism for clamping onto the raceway. Ground fault circuit interrupters, or GFCIs, are devices that are designed to protect people from electrical shock hazards. GFCIs work by monitoring the current flowing in a circuit and detecting any imbalances that could indicate a ground fault. If a ground fault is detected, the GFCI will quickly interrupt the circuit, preventing electrical shock. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas. Arc fault circuit interrupters, or RFCIs, are devices that are designed to protect against fires caused by arcing faults. RFCIs work by monitoring the current flowing in a circuit and detecting any abnormal arcing conditions. If an arcing fault is detected, the RFCI will quickly interrupt the circuit, preventing a fire from starting. RFCIs are required in many locations, such as bedrooms and living rooms. Surge protected devices, or SPDs, are devices that are designed to protect electrical equipment from voltage surges. SPD work by diverting excess voltage to ground, protecting sensitive electronic equipment from damage. SPD are often installed at the service entrance and at individual pieces of equipment. Electrical systems in healthcare facilities, especially critical care areas, require special attention to grounding and bonding to minimize the risk of electrical hazards to patients and staff. These areas often have sensitive medical equipment that can be affected by electrical noise or leakage currents. The NEC provides specific requirements for grounding and bonding in healthcare facilities in Article 517. These requirements are designed to ensure a safe and reliable electrical system for patients and staff. Isolated power systems are used in some critical care areas to further reduce the risk of electrical shock hazards. Isolated power systems use a transformer to isolate the electrical system from ground, preventing leakage currents from flowing through the patient. Line isolation monitors are used to continuously monitor the impedance from the ungrounded conductors of an isolated power system to ground. If the impedance falls below a certain level, the line isolation monitor will alarm, indicating a potential ground fault. Core potential grounding systems are used to minimize voltage differences between different metal surfaces in a patient care area. Equipotential grounding systems involve bonding all metal surfaces together to create an equipotential plane. This reduces the risk of electrical shock if a patient comes into contact with two or more metal surfaces simultaneously. Regular testing of electrical systems in healthcare facilities is essential to ensure that they are functioning properly. Testing should include ground impedance testing, leakage current testing, and insulation resistance testing. Testing should be performed by qualified electrical professionals who are familiar with the specific requirements for healthcare facilities.